we continue discussing how congestion control is implemented in the internet. We left at this point last week. We saw that TCP implements an approximation of additive increase when there is no loss by increasing the window by a fixed amount every round trip time. And when there is a loss detected by timeout, it goes into slow start until it reaches half of the window size that was just before the timeout, which is one way of implementing the multiplicative decrease. This is what is shown here is not a typical case because, as we know, detecting losses by timeout is not very efficient in TCP, and most losses are believed to be detected by what is called fast retransmit, and associated with that is fast recovery. So fast retransmit, if you remember, is detects a loss when we receive a number of duplicate acknowledgements, where we call duplicate acknowledgements an acknowledgement field where the bottom part of the acknowledgement field is not moving here. Now, there is a problem with this that occurs in exactly this case, which is illustrated here. TCP controls the rate by controlling the window size. So when we want to reduce the rate, we reduce the window size, and this is based on this formula here. But this formula is true only in periods of time when there is no loss. What happens when there is a loss? When there is a loss, depending where in the window the lost packet is, the sender is blocked from sending at the packet that is lost here because of the principle, the mechanism of the sliding window. So just applying this brutally could result in blocking a sender instead of reducing. If we run a window by 2, in fact, it might even be that the sender cannot send any packet at all if the packet that was lost is towards the beginning of the window. So assume you have sent 10 packets, the window of size 10, then we reduce the window to 5, and that means you can only send 5 packets from the largest acknowledgement that has been received in sequence. So if there is a packet missing, if packet number 2 is missing, for example, that means you can send only from packet 1 to packet 6, so which you have sent already. So essentially you block the sender. So this is where the to control a rate and the mechanism of using window for that, they collide. They don't work well together. So if you would just do the multiplicative decrease when there is fast retransmit, when we detect a loss, we say we divide the window by 2. If we just do this, in many cases, it would not work very well. We would, in fact, block the sender. So instead of to avoid this problem, a heuristic, which is completely heuristic and ad hoc, has been devised that is called fast recovery. And it consists in saying, whenever we detect a loss in this way, we put a target window, which is called slow start threshold in TCP code, which is half of the current size. This is the multiplicative decrease. But the actual window that we set now is increasing exponentially, starting from a value which is this plus 3 packets. So essentially, we take this threshold plus 3 and we increase exponentially until the packet is until the loss is repaired. I think the easiest is to explain this on an example. Here is a cartoon that is showing a number of transmissions from the sender on the left. Packet number 2, packet sent at time 2 is lost here. So some acknowledgements will be received, and we will see that the acknowledgement field here does not increase because it's stuck at number 201, which is the first byte of packet 2 that is missing. Of course, there is in this packet certain acknowledgement fields that will help the source to know which packet is missing and which not, so that the source does not retransmit things unnecessarily. But this is not used by congestion control. Congestion control uses only the acknowledgement field, which I recall is has the semantic of cumulative acknowledgement here. So the window has a size of 800. So in this toy example, that means 8 packets. The congestion window is equal to the slow start threshold window. This is what happens in the normal case for TCP congestion. Then here at this point, a packet is acknowledged, so the congestion window is increased by 1 over the window size. That's the additive increase approximation that is done by TCP. And here the following packets are not new acknowledgements, so they are ignored. They don't increase the congestion window, but the window is large enough. We can send 3 more packets until at this point here we receive an acknowledgement, which is a third duplicate. We have received 3 times the same acknowledgement field and +1. So if the TCP max duplicate acknowledgement threshold is set to 3, that means it is the third duplicate. The first one is not a duplicate. This is the first duplicate, second, third duplicates. So here we do fast retransmit. Here we say, oh, there has been a loss. And therefore, we apply this method here. The method says we take the slow start threshold equal to half of this, rounded here. That gives the target window. And the congestion window is this plus 3 packets. Here, the MSS, the maximum segment size, is assumed to be 100, which is very atypical. It is never that small, but that's to make the story simple here. And that's the crux, because if we observe here, if we had set the congestion window to 407, if we had just done the multiplicative decrease, the congestion window would be 4, and we are stuck at 2. That means we can send packet 2, 3, 4, 5, which have been sent already, which means we would be de facto. We can retransmit a packet, but then the source is blocked if we would put it to this here. But that's not the case here. We allow 3 packets, so the source can continue sending, which is happening here. And then this is the packet sent at time 13, the repairing of the loss here. This repairing is received and acknowledged at this time here. So at this time, this is the end of the fast recovery. And in the interim period, we see that the congestion window increases by 1 packet for every duplicate acknowledgements that is received here. So we allow, by receiving acknowledgements, even if they are duplicated here, this is taken as a symptom that there is something coming back from the destination. So we increase the window to give the possibility to the source to send more until it is repaired. And when it's repaired here, then we set the congestion window to what was the target, 400. But now there is so we can send from this one here. We can send from the bottom of the window. In fact, that's the question. How many at this, if we continue the simulation that is here, how many new segments of size 100 bytes can the source send at this time here? I'm closing the poll in a few seconds. Closing. And the majority says 2, which is the correct answer. Here, the congestion window is 400, which in round numbers is 4 packets. And the sliding window allows to send everything since the acknowledgements. That means we can send 4 packets starting at byte 901. So a first packet has been sent already, which means we are allowed to send 3 more. We can send 3 more packets here. So this is how it works. It is a bit ugly in the sense that there's a number of constants in this algorithm, and it's not very clear whether they are optimal constants, and probably they are not in general. We need to adapt them, but this is not done. And this illustrates the mismatch that there is between controlling the application, the rate versus controlling the window size. We'll come back to that when TCP-BBR attempts to modify this, but does not really succeed either. Another question. Assume we use Wi-Fi and we lose it. Because of the Wi-Fi transmission error, what will happen? I close the poll in a few seconds. And here, clear answer. The answer is B. The TCP source doesn't know whether a loss is due to transmission error or anything else. When something is missing, the only thing you know it's missing. Why is it missing? Well, you need to work hard to know why it is missing, and TCP has no information. So TCP will think it's a congestion loss and will do a window reduction, depending on the loss is detected. If it's detected by timeout, it will go into slow start. If it's detected by fast retransmit, it will go into fast recovery. And that's a fundamental problem, but which is unsolved today. This is why, if you assume you have a Wi-Fi and you're transferring something from a very busy server somewhere, you are competing with other flows to get to this server, and your competition is controlled by TCP. We will see that TCP is very close to additive increase, multiplicative decrease. So we see it's optimizing a utility. So if there is a bottleneck somewhere between you and the server, for example, in the access of the server to the internet, you will receive your fair share of this bottleneck with TCP in the sense of utility fairness implemented by TCP. This will not if there would not be the Wi-Fi losses. But if there are the Wi-Fi losses, then you will receive much less because your TCP is reducing the window very often if the Wi-Fi losses are very frequent. So your performance will be poor. Not so much because the capacity of your Wi-Fi is small. Perhaps you have a 100 megabit per second or 500 megabit per second Wi-Fi link with losses once in a while. So you will be able to download at 100 or several hundreds of megabits per second from a remote server, but you won't because you are competing with others for a bottleneck and you receive wrong signals indicating that your source should reduce the rate dramatically here. This is why, if you're gaming, you will do it on Ethernet and not on Wi-Fi. This is why also, if you care about transmission and transfer quality, you may still prefer Ethernet than Wi-Fi. This is also, the same is true for cellular networks. This is why, for example, for cellular networks, there are several optimizations that are done, essentially content caching. Instead of downloading it from the wide internet, you will download directly for something that is in the domain of your cellular telephone operator, so that your competition is between all people who are on wireless systems, and you're not competing with somebody who is on Ethernet. The cellular network operator will prepare the work for you. So that is one of the side effects of how TCP and congestion control in the internet is today. And the only solutions, as I said, are content caching. I mentioned fairness. So TCP implements an approximation of additive increase, multiplicative decrease. So it is also, we can do the analysis of how it leads to a utility. So utility is a bit different than the one we had for additive increase, multiplicative decrease, because the the increase is a bit less than linear. So, but it doesn't really matter if you plot the AIMD in blue versus Reno in red, you see it's quasi the same. Of course, I plotted the curves by rescaling it at one point, so starting some same initial value, because utilities are just relative. It's only the relative value of utility that matter. So take-home message, in practice, it doesn't matter, at least for a fixed RTT here. That's the theory of utility works. So in some sense, TCP is a first approximation, but we'll come back to it in a second. First approximation, we can consider that implements a form of fairness, so sharing, which is satisfying all the axioms that we have seen last week, close to proportional fairness, a bit tweaked, a bit biased towards max-min fairness. However, that's only the first approximation. Now let's go to the more details. However, there's a big however. There is round-trip time that plays a role here, because the fairness that we see here with this function, the utility function, is 1 over the round-trip time here. So which means the utility that is allocate everything, of course, it does not happen with a central allocation, but the distribution of rates, when you have a number of TCP connections, TCP Reno connections, is as if there would be a central allocation system that would allocate to every flow a rate such that the total utility, the sum of those functions of the rate X, is maximized. We did such exercises for proportional fairness, so it's the same here with arctangent instead of logarithm here. However, in the function, there is a round-trip time here. So the utility depends on the round-trip time. And here is, it's hard to see just by inspection how it works, because this is decreasing with tau, and this is increasing with tau. But arctangent is a very concave function, so it the increasing function part here does not win against this part here. So this is a map of this function if I fix tau for a given value of x, right? For x given this one. So we see it decreases with tau. So the utility that is allocated to you is a decreasing function of your round-trip time here. What does it mean? For example, if I have two sources that are accessing content from a destination over the same bottleneck, but with different access times, perhaps because they have different links here. They access over a network that is not congested, but has much larger delay for this one here. So the round-trip time is proportional to 30 and 70 here, if we ignore the queuing time here. So the round-trip times are 60. If multiplied by 2, they are 60 and 140 megabit per second. What do you think will happen? Will S1 get the higher throughputs than S2? Will S1 win the competition, or S2, or will both get the same? I close the poll in a few seconds. Closing. Majority says A, which is the correct answer. Why is it? Well, imagine for a second you are this virtual bandwidth allocator or rate allocator in the internet. You need to allocate to S1 and S2. The bottleneck here, there's only 1 megabit per second to allocate. Those two sources, they would like to have up to 10 megabit per second each. If you want to implement max-min fairness, you would implement half of this with the water filling algorithm, we'll see we increase the rate of everyone until we have a limit of half of this, 500.05 here. But we're not implementing max-min fairness. We're implementing this fairness here that has a utility that is decreasing with the round-trip time. That means for x, the utility of S1 is larger than the utility of S2. So you have to allocate this x, which is 1 megabit. You have to allocate to 1 and 2. 1 gets more utility when you give x than 2. So you will give more to x1 because when you sum the two utilities, there's more benefit here. It's not linear. If it would be linear, you would give everything to S1. The utility is concave. So at some point, you have to stop giving more to S1. When you reach the point where of diminishing returns, you still need to give something to S2. And this is exactly what we can see. This is the result of the kind of measurements you will do in Lab 5 when we watch over time how much packet bytes have been delivered by S1 and S2. We see for this experiment, we will see something like this. We see that S2 gets, roughly speaking, twice less than S1 here. This is known as the RTT bias of TCP. TCP has a bias against large round-trip times here, which is, again, it's not a desirable behavior, it's the result of the way it is here. It is sometimes misinterpreted as something desirable in the sense that if I have a source, you remember the kind of exercises we did in the past weeks, we looked at a source that is using 4 links, whereas another source is using 1 link. Then we say it makes sense to give less throughput to the source that is using 4 than the source that is using 1. That was the principle or the axioms of proportional fairness. And TCP will do something like this. It is true. And if you use 4 links, it is likely that your RTT is larger than if you use 1. Most of the time, this is what happens. So in some sense, there is a correlation between large RTT and usage of resources, which justifies that if you have a large RTT, you receive less in the sense of proportional fairness. It's correlation, it's not causality. It is not because your RTT is large that you should receive less. It is your RTT being large is probably correlated with the fact that you use more resources and therefore you should receive less. So this is one of the root causes of the misunderstanding of why sometimes you read some people who are happy with this bias here. But this is, so part of it is inevitable. It comes from the utility maximization framework, but part of it is a true bug, and it has to do with the fact in the example we gave before, the two sources are exactly in the same position with respect to the bottleneck, except this cable here is longer. So there's no reason this guy gets much less than this one. The bottleneck is here, they should receive exactly the same. Now there is a physical reason. It's in the way TCP implements additive increase, it's 1 packet per RTT. So if your RTT is large, the rate increase is smaller. You increase by 1 packet per 10 millisecond or 1 packet per 100 millisecond. So if you have a large RTT, you are doing additive increase and multiplicative decrease, but your additive increase is smaller. So you compete with others who have a larger additive increase. So not surprising, they will get more. In fact, we can quantify exactly this by what is called a simplified loss throughput formula. What is a loss throughput formula? Well, it is a formula that captures approximately, very approximately, the relation between the throughput that an ideal TCP connection would get when it receives a certain loss rate here, loss probability. So if you loss probability means, for example, if it's 1%, I mean 1% of the packets are lost. And what I mean by ideal connection, it's a connection that is very long and has a huge amount of data to transfer. If the connection is very short, if you have only 3 packets to transfer, let's say 10, then most of the behavior is in slow start at the beginning. So the performance is a bit different. But if you have a huge transfer to do, you're transferring a movie of 1 gigabyte, for example, then you will see this. This formula maps the throughput that you can obtain. Also, when I say ideal connection, it's large and has the large data to transfer, and also it is not limited by anything else than TCP. In practice, a connection might be limited by other things, like what? Well, the hardware, the incarnation of the environment in which we are. If you're working on a high-performance computer with offloading to the hardware, you might have 1 or 2 gigabit per second as the physical maximum limit of the transfer. If you're on a lower performance device, the performance might be even less. So there is the limitation of the hardware of the environment, and you might be also confronted with other sharing problems. For example, the operating system might be very busy or congested. Your application might be busy and not able to consume the data at this rate here or generate the data at this rate. So there is usually other limits, but this is about the rate that you would have if the limit is only TCP, congestion control in the internet. And this formula says what? It says if I observe over a connection loss probability Q, then the throughput will be given by this. We see that if Q is equal to 0, the throughput is infinite, which is consistent with this ideal connection model. If there is no loss, that means there's no limit. There's never any negative feedback from the network. So there is no limit on what this connection can send. So the theta is infinite. And if there's 1% loss, you will have this. MSS is the packet size. 122 is a universal constant. And RTT is the round trip time. So this captures exactly the bias of TCP Reno against RTT. If your RTT is larger, then your maximum throughput you will get is smaller. It also captures another one. I mentioned the bias against RTT. There's another bias, which is in favor of large MSS, because we increase the rate every round trip by 1 packet size. If your packet size is large, the additive increase that you obtain is also larger. So there is also a benefit in this competition among sources for sources that have larger MSS here. Equipped with this, are we able to say a bit more? So we take the same example as before and try to guess what is the ratio between the throughputs that S1 and S2 will get here. I'm closing the poll. Closing. And the correct answer is C, which is also the majority vote. It is inversely proportional. If we apply the loss throughput formula, the loss throughput formula will say us, well, those two connections, as I'm assuming they have the same MSS, and they will have the same drop probability because the drops will be only on the output of this router here. In general, of course, different connections will have different drop probabilities if they have different paths. But here, if the router is fair, is dropping probability with same for all flows, then they will have the same drop probability. Then everything is the same except the MSS, the RTT, and the throughput is inversely proportional to RTT, which means we have this equality, which leads to that, which is more or less what we can observe here. This formula was used in what is called TCP-friendly UDP applications. Remember that congestion control must be done, at least for all long-lived flows, for flows that generate significant amount of traffic in the internet. because otherwise the internet will be inefficient, will go into congestion collapse, and all such bad behaviors. Now, if you have UDP applications that are not using TCP, if it's quick, for example, we'll say a few words about quick in one of the coming weeks. Quick is not really an application, it's a replacement for TCP. So if you replace TCP by quick, quick runs on UDP, so UDP does nothing. So it's quick that should do the same thing that was done by TCP. So that's an example of a UDP framework, or an application that uses quick is a UDP application. Then it must do something like TCP, and the way it does it is by quick imitating TCP. We'll talk about quick very soon. So essentially, quick does exactly the same as TCP. It doesn't imitate, it does exactly the same as TCP. Now, applications. And there are other applications, for example, applications for video transfer that are over UDP, not because they use quick, but because they do very different things. For example, they don't repeat lost packet. If a packet is lost, you don't repeat it. Instead, you hide it. I mentioned that already. Some smart video coding applications will encode a certain packet several times, one with a low resolution framework, another one with a high resolution, and they might send a high resolution in a different packet than the low resolution. So that if a packet is lost, what you would do is try to hide the loss by recovering the low resolution and displaying it instead of repeating. You can also do more radical things like interpolating. If you have if you receive 10 frames every second for video, and if 2 frames are missing, perhaps the smartest thing to do is to interpolate the 2 missing frames from the ones that you have received before and after, given that when you play video, at least for not very interactive video, you use a playback buffer that gives you some time between reception of packets until displaying on the screen. So when you display on the screen, you wait perhaps 20 to 30 seconds so that you can accumulate a number of data in the buffer, and then you can do those things which are more efficient because they don't involve perturbating the source and work in particular in multicast mode. So if you have such an application, then you cannot imitate TCP, because quick has a window, a sliding window, and all the stuff. So it does the same essentially as TCP by not exactly the same. It's a bit better. But here, there's no sliding window. You just send frames that are coded with multiple resolutions and combine it a bit like you do coding when you use Reed-Solomon codes. For such applications, one technique, which is specified by one standard called TFRC, TCP-friendly rate control, is based on this formula. It consists in sending, this application adapts the sending rate. So video applications typically do that, not by a window, but by truly a rate. So they count how many bytes or bits are sent every second, and they control this amount here, whether there is loss or not. They control the sending rate, not a sliding window. And this is what a video application does now, because it needs to decide on a coding rate, right? If I code for high quality 4K video, I will have several megabits per second of resulting outgoing rate. If I code for a single SD resolution, for example, I will have a coding less than a megabit per second. So the rate is directly controlled by the video coding rate here. So we can control the rate in this way. Then such applications will require receive back not in the form of acknowledgements, but in the form of counts of lost packets. And with that, we can estimate the drop probability Q. We require that the destination reports every second what is the status of what has been received. From this, we can count how many packets were dropped and estimated with using various estimation methods. And then the source simply sets the rate to this value here, given by this loss throughput formula. So we set to this rate, and then we try to find a coding that is as close as possible to this one and does not exceed it. So in some sense, such an application pretends to be TCP by pretending to follow exactly the loss throughput formula. So that's one of the uses of this loss throughput formula, apart from giving you exercises. Well, this is the state of the art on TCP Reno. Since TCP Reno has been implemented, there has been hundreds of variants of TCP because people have kept being unsatisfied with how it is. With everything we do here is very approximate, and we will see two variants of TCP, which are cubic and data center TCP. We'll say a few words about also BBR. Cubic is a variant of TCP Reno. So when I say variant here, I mean a variant of the congestion control algorithm. So the TCP itself is the same. We're talking about how the congestion control is updated. Now, TCP Reno has a number of shortcomings. I mean, can you see a few? Can you imagine a few? Well, one of them is something we've seen on the simulations in the past weeks, where we see the reduction is by 1/2, right? If we lose a packet due to something, we reduce the rates by 1/2, which is a very severe thing. If you think about it, if we're trying to, so in the hypothetical case where I simulate on the AIMD, we've seen that this produces very large oscillations here. So this might not be the most efficient thing to do. But there are a number of other shortcomings that have been measured. Of course, there's the RTT bias that we have mentioned, which is not nice if you're very far away. It's if you are rigorously accessing the network and you are very far away from the thing that is serving you, probably you'll be in a very bad position because you combine two handicaps, very large round trip time, and second, spurious loss signals, negative signals, that have nothing to do with congestion, but that you must interpret as congestion signals. So TCP over large RTT really does not work. Will give you very poor performance. So if you access the internet over satellite links, for example, Starlink or things like this, then you will very probably have to rely on content caching. So, which is at the end of the satellite link, so that you compete only with others who are on the same satellite link and not with the rest of the internet. Another thing here is what we call self-inflicting delays. If network buffers are large, TCP will fill the buffer before adapting the rate here. In all these examples, pretend the RTT was constant and given by the number of the hops and the technology. But in reality, the RTT is dependent on the queuing that is in the buffers. If there is a lot of packets in a buffer, then the queuing becomes larger and there is a large delay. Now, a large delay is bad for lots of reasons. But in particular, if you combine on the same link interactive short flows with large bulk transfers, for example, you're doing a backup of your Dropbox, and at the same time you're trying to watch a video, have a Zoom session, then you will have a huge, and if you have, if your router at home has a large buffer size, which is probably the case because the speed that the router is working, buffer size is very cheap, so it will probably have seconds or even tens of seconds of buffering here. Then the delay, those packets, those buffer will fill, and then the interactive delay will have, the interactive flow will have 10 seconds of added round trip time simply because your router has full buffers here. That's one of the issues that we will discuss a bit later here. There is another issue which is very specific to what is called long fat networks. Those are networks that are not typical for common users like you and me, but that happen if you have long means very long propagation time, and fat means you have high bit rate here. So if you have gigabits per second over the Atlantic, This is what Google has when they do, for whatever reason, if they want to transfer some data from one data center to another one, they have to transfer this huge amount of data across the Atlantic, for example. Then they are using what is called a long fat network. It's not very frequent for each of us because when we access the internet, we typically are in competition with others. So even if the links are multi-gigabit per second or hundreds or even thousands of gigabits per second, we are also competing with hundreds of thousands of users. So what is available for my TCP connection is not that much. But this is true if you are a company like Google, or if you're at CERN as well. If you're transferring data, you do experiments in trying to find whether the Higgs boson really exists or not. So you have millions of samples per second that are generated, and then you want to send that to physicists at the other part of the world, or even inside CERN from one location to another. So you have huge transfer rate over distances that are not extremely small. This is what happens if we use TCP. This is a figure assuming the MSS is this value here, and the RTT is 100 millisecond. And if you have links of gigabits per second. So a single TCP connection is able to get gigabits per second with an RTT of 100 millisecond. Those are the numbers at which this phenomenon will occur. Then you see we start with slow start here until we get the certain, we hit the capacity of the link. Then we will decrease in some form, either through the target window directly or whatever. But if I ignore the transient phases here of fast retransmit here, we will still, at the end of fast retransmit, restart with half of the value, and then we increase again with no loss until we get there. And it turns out that this increased time for those numbers is very large, is order of an hour here. So if I zoom on this, or this diagram here with those numbers is very different from the ones we had before, where we saw oscillations around the optimal value. Here's the same, except the oscillation period is hours here. Why is that not efficient? Well, because when we are doing that, you see that all this area is unused. I mean, we have capacity, we have 5 gigabits per second here, but half of this capacity is not used for a short amount of time. But in average, the rate we get is halfway between 5 and 10, so around 7.5. So we're wasting 7 gigabits per second of capacity simply because we're not increasing very fast. It would be better if we would do multiplicative increase. But if we do multiplicative increase, we have a problem. The theory of LRMD says to you, during the increase phase, you should do additive and not multiplicative, because otherwise you will not achieve any form of fairness. So we have a problem here. This is the problem that is being solved by what is called TCP cubic, which is, I would say, the most frequent implementation of TCP congestion control. So probably all devices we're using is using TCP cubic or a variant of it. The TCP cubic is also heuristic. It starts with LRMD. So, but it will modify it by a cubic phase here. Here I'm showing, as a function of time, the size of the congestion window just after a loss. And I ignore whether we go into slow start or fast retransmit. I assume it goes very fast. And at the end of this, we reach half of the window before. So before there was a loss, we had reached a certain congestion window. There is a loss, we divide it by 2, and then we increase linearly. This is additive increase, more or less Reno. Reno is doing a bit less than this, but this is what the theory says it should do here. Well, the idea of cubic is to say we will create a function of time, W of t, which is this blue curve here, that has the following properties. First, it starts not at 1/2 of the congestion window before the loss, but at 70% here. So we do LRMD, but with a decrease factor of 0.7 and not 0.5, which is a little bit better because the oscillation will be less bad as before. And then we implement this magic function, which is a function of degree 3, polynomial of degree 3. That's why it's called cubic, which is given here. It's a function of time, which has a property that it starts at at the value W of 0, which depends on a parameter k, where k is computed such that we start at 0.7. And then k is the time at which we will reach the flat part of the cubic curve here. And when we reach that flat part is exactly when we have reached the W max here. So the heuristic idea is that we increase, in fact, in a concave way, because the cubic function is concave at the beginning until it reaches its inflection point here, and then it becomes convex, which is the computer science view of first we start slowly until we reach W max, which was the same as before the loss here. And we continue to increase these levels. So the idea is we are conservative at the beginning, similar to additive increase. We increase slowly. And if we reach to higher, then we do take advantage of this to go faster here. So we try to be conservative at the beginning until we see it works, and then say, yeah, we can increase more rapidly here. This is the theory. Now, this theory, I've shown it on a nice case when the RTT is 0.1 second, 100 millisecond, which was the typical set point where cubic was seeing the problem. But in reality, depending on the size of the window also, we can be in this or that situation. So because this is cubic, this is linear, they are not in the same, behaving in the same way. They do not scale in the same way. So it could be this or that. So it could be that it is less fast than additive increase, or it could be that it is faster than additive increase here. And in order to address this, cubic wanted to be not more aggressive than TCP-Reno when we are operating in this region where we will not be able to increase dramatically. So it does it by taking the minimum of what TCP-Reno will do and the formula that we saw before. So if the W of t is less than the TCP-Reno, then cubic will replace W of t by TCP-Reno. With a catch here, that cubic decreases by 0.7, not by 0.5. So what happens if you have two versions of TCP-Reno? One that says whenever there's a loss, I do everything like we said before, except the target window, the slow start threshold, is not equal to 0.5, the window that we have observed at the loss event, but 0.7 will we obtain a version of TCP-Reno that is less aggressive or that is more aggressive? Well, it's more aggressive. If you give me the choice of being reduced by 30% or by 50%, I prefer a reduction by 30%. When there is a loss, I reduce less, and I will start from there. So it works the same way. The theory of AIMD doesn't say that the decrease should be 0.5. With any value of the decrease, we will have the same theory with different loss throughput formula. The loss throughput formula that we saw can be found also if we have a decrease term of 0.7. Now, if I do the decrease 0.7 and the increase is the same, of course, I will have a throughput that is larger because I decrease less and I increase the same. But we can compensate for the decrease being larger, not as bad, by having an increase that is smaller. And by how much should we compensate? Well, we apply the loss throughput formula with generic values of increase and decrease, which is easy to obtain. And we find that if you want to compensate, then you should increase by this quantity, which means for every packet, by every rental time, you should increase the rates not by 1 MSS per RTT, but by 0.529 MSS per RTT. And cubic does all this zoo of details here. So when cubic compares to AIMD, it compares to this version of AIMD. So cubic implements both the cubic increase and the AIMD increase. And it with those parameters, and it takes the minimum of the two, which means that it will always get at least as much as the throughput that we would have with AIMD, with equality when the RTT is small here. People did a calculation of the loss throughput formula. This is That's the loss throughput formula we have for AIMD, for TCP Reno. Now, that's the loss throughput formula we obtain if we do the zoom modification that Cubic is doing, which is given by this. Now, we see that Cubic in its formula, in this formula that is given here, is independent of the round trip time. So the increased term here is independent of the round trip time. So it will try to avoid the problem of the round trip time bias that TCP Reno has. As we see in the loss throughput formula, it does not entirely get rid of the round trip time. So the RTT plays a role, but with a power 0.25, which is a very concave function. So it's much less severe. Why is there still a dependence? Well, because the round trip time still plays a role in clocking the system. If we detect things once per round trip time, in particular, the negative feedback is obtained at a clock that is given by the round trip time. If the bit rate and the RTT is large, so in particular when the bandwidth delay product is large, of course the TCP Cubic connection is expected to get more than TCP Reno. That's the job goal that was given to the development of TCP Cubic. That's the goal of TCP Cubic here. In practice, when the bit rate or the RTT are not both large, which means for us in the lab, for example, TCP Reno or TCP Cubic give the same thing. And where exactly you want to be is given on this diagram. Here on this diagram, in red, you have the throughput that is obtained by TCP Reno as a function of the loss rate. This is in logarithmic scale, so it gives a linear thing. So this is plotting this function in logarithmic scale with a slope of 1 minus 0.5 and plotted for different values of the RTT here. And in blue are the formula given by Cubic. If Cubic would not cap to the minimum would not have this comparison to AIMD, and Cubic will get the best of both here. So if we are in this region here, we will get, Cubic will get less. So we see it is when the throughput is orders of hundreds of megabits per second, and the RTT is 10 or less millisecond here. Oh, there was no feedback in the room about the, sorry for the excessive delay. So we'll take care, by the way, of buffer bloat and additional delay in a few more minutes. But let's do a break and let's resume in 10 minutes. So Cubic the problem that I explained here, that I mentioned a few minutes ago, of self-inflicted delay. Another symptom of this is called the buffer bloat syndrome in this paper. This is shown as a function of the window size. On one axis, vertical axis, the rate, and on another axis, the round trip time here. So assume you have a flow, and then you start from slow start or something like this. And the rates that you can have for TCP will be dictated by some physical limit. We can think of it as a bottleneck. In a simplified view of the network, there's only one link that is more congested than the others. You call it the bottleneck. And what happens with when you do all the methods that we have seen so far? So you increase the window, and as you increase the window, at the beginning, the rate that the connection has is less than the bottleneck capacity. And as you increase the window, you get to the bottleneck capacity. And as you increase the window, you continue increasing the window, the rate that you receive is not increased because there is a maximum limit to the physical limit. But if you don't have this limit, you continue increasing, and you don't see any benefits in the delivery rate, the useful throughput of your TCP connection. But what happens when you continue increasing the window? Well, in fact, you start filling the buffers on the path. By filling the buffers, you increase the round trip time. Here, right? Until you get a loss, because the buffer is full, and then you stop increasing the window and you start here. So the operating point that you will have is here with such a scheme. We stop increasing when we are faced when we find a loss here, which is probably when the buffer is full. The ideal operating point should be here. If we care about delay, we should stop when we've reached the bottleneck link capacity, and there is no point sending more into this buffer until the buffer gets full if the link speed at the output of the buffer is not sufficient here. So we would like to operate here. We would like a mechanism that increases the window until some magic we know there's no value going beyond here. And this is not what we do with what I've presented so far here. So there is a way to reach that, which is called ECN, explicit congestion notification, which is as old as additive increase multiplicative decrease. It was implemented already in the DECnet networks under the name of the DEC bit, and was the secret weapon of digital for why their networks were performing way better than any other network. It was better than IBM, better than TCP-IP, better than the internet, better than the novel netware and all the Microsoft-oriented architectures. If you remember, analysis of AIMD is assuming that we receive a feedback, and then we said in the internet the feedback is a loss. Fine. But what if the feedback is a true bit of feedback, not a loss, but a bit that you have somewhere in a packet header? That is the idea of ECN. So the idea is that routers on the path mark packets instead of dropping, and destinations echo the mark back. Of course, the routers will not send feedback directly to the source. That would be too expensive. We don't want routers to do that. That would mean whenever a router starts to be congested, we need to generate a message in the reverse direction. It's a bad idea because when you're congested, you want to simplify the work, not give more work to a router when it's congested. So what it will do is simply flip a bit in the header of the packet somewhere. We will see it's in the IP header. And that needs to be returned to the source, and this is returned in the TCP header back to the source here. So this is how ECN works. I'm assuming here a source is sending a packet. ECN using the combination of the TCP header and the IP header. Assume a router starts to be congested, so the output buffer of a router is congested. Then we will flip a bit somewhere in the IP header. It's one of the reserved bits that we have not discussed so far. So one of those bits will be marked here. And when the operating system destination receives it, it says, oh, this congestion experience bit is marked here. So it will be written into the TCP header. In the TCP header, there are also 2 bits that can be used. So it will, or 3, if I remember well. And that will be in the return channel, will be sent as a TCP header, unchanged by whether there is congestion or not on the TCP path. Here is irrelevant. This is part of TCP, not of IP. And now when the source will receive this, it will say, oh, this packet is marked here. And the source will do LLMD, decrease the window by exactly as we have discussed before. So instead of it will apply exactly what it would do by reducing the window by half if it's using Reno, by 0.7 if it's using or by 0.7, and will apply the cubic thing. Now the difference, of course, is there's no loss. So we don't need to do fast recovery, and we don't do into slow start because there is no packet loss. We send a signal back to the source saying, now you should reduce. I haven't blocked your packet because I am smarter than that. I'm sending you a signal. You should reduce the rate. So here is a replay of something we said we saw last week. Can you put the labels correctly? So I'm showing here the window size that is increasing, decreasing, increasing, decreasing, and I'm assuming I'm using ECN. Can you put the labels correctly on this figure? Closing the poll in a few seconds. Closing. And the correct answer is the majority vote. So when we see no mark in the packets, we do congestion avoidance, which increases linearly. And when there is a mark received, then we reduce the window by 1/2. But since there is no loss here, we don't need to do any sophisticated thing because there is no packet loss, at least not due to congestion. With such a system, we can two bits, 1 bit in the IP header, 1 bit in the TCP header. In fact, we have 2 bits of each for reasons that are a bit long to explain. I will just give some of the reasons. So the bits in the IP header are called the ECT, R2. One of the reasons is that we need not just to mark whether a packet was seeing congestion or not. We also need to mark whether this flow is implementing ECN or not. Because if a source is not implementing ECN, your version of TCP does not react to ECN, but only to drops here, what will happen? Well, if you have a router that is nice and sees a packet and sees, oh, my buffer is starting to get full, I will mark all the packets. But for those flows that are not following ECN, this has 0 effect. They will not reduce their rates. So they will reduce their rates only when there will be a loss, which is bad for those who are behaving well and reducing their rates because they saw marks. Eventually, they will also see losses here. So typically, routers will tend to give differential treatment to flows that mark ECN, that respect ECN or not. So we ask the source to put a bit saying, are you ECN capable? So do you do ECN or not? Of course, this is old-style internet. This is assuming everybody is well behaving. Le pays des bisounours, right? In fact, you can say, I am implementing ECN, and you don't implement ECN at all. So your packets will not be dropped. If you're the only one doing that, you will see very good performance, much better for performance than everyone. If lots of people are doing that, then ECN will not work at all, and that will not work well. So because of that, there has been a very complicated way of randomizing the way the mark is given to try to infer whether the source is really implementing to reacting to ECN or not. So this has consumed 2 bits. This has been deprecated, has been deployed a bit, but this is used typically today in a different way. As we will discuss, the routers will tend to segregate the traffics that respond to ECN or not here. So ECN is very useful, in particular in the wireless domain, in the cellular telephony domain, where this is implemented by routers. And you will see also that there are various versions of TCP that react differently and use ECN bits differently, in particular cubic and DCTCP. The story I gave is about cubic or Reno, that practically are the same here. We'll see in the second DCTCP that does things a bit different. Also on the TCP header, a little bit of feedback. And in fact, there is a second bit of feedback. This is to guarantee, at least approximately, that the source reacts to negative feedback once per RTT. If you react to any negative feedback you receive, then you will decrease by a factor of 2 or by 0.7 the window many times, which is counterproductive. That's not what you want. So the theory is rate-based and assumes every RTT will receive feedback here. So this reason for 2 bits is to implement this. Essentially, one of the bits is used as an acknowledgement by the source that it has seen the congestion bit and that it has implemented the decrease here. How does a router know it has to mark a packet for feedback? Well, it needs to use what is called an active queue management function. Active queue management is something that looks at the queue statistics and decides when to mark a packet or not. So The very popular active queue management is RED, random early detection, which takes an average queue length with this exponentially weighted moving average here that tries to filter out a bit the variability of this. So we measure the queue size here, we plot it on the x-axis here, and as a function of this function that is given here, this highly nonlinear function, gives you the marking probability. So if the queue size gets large, you mark all packets. If the queue size is very small, you don't mark any packet. And this is the region where you would like to operate. And when you operate in this region, you mark only a fraction of the packet by flipping a coin. If you say the marking probability is 10% for every packet, you will flip a coin, and there's probability 0, you will mark the packet or not. It's a bit more complicated. You don't really flip a coin. You also make sure you don't, because if you flip a coin, you might mark 2 packets in a row, so you also manage the spacing between packets. But those are details we can ignore. So essentially, this is where we would like to operate. We keep a P that is not too large, and the average queue size will remain within this region here. Active queue management is necessary if you deploy ECN, because you need to know when to mark a packet. So the router needs to have this background task. It's not a real-time task. You don't need to do very complicated things for every packet. You just monitor the queue length once in a while, and you do this measurement. And what you do in real time is to mark the packet or not here. So it's necessary for ECN, but it is also deployed. In fact, even if you don't have ECN, in this case, RED is used to give the drop probability, not the marking probability. Now that seems counterintuitive. Why would you decide to drop a packet here if the queue size is not full here? This seems paradoxical, but there's a good reason for that. And the reason is, again, to avoid the buffer bloat syndrome. If you send if you drop a packet, you're giving a signal to the source that you should reduce here. So that's a way to avoid that the sources will go to the operating point that I showed a few minutes ago, that they will stay closer to the end operating point where they receive drop signals, because the queues will already reduce their rate here. So the belief is that one, and it has benefits even if we don't deploy ECN. When you do this, you say that you do active queue management. The opposite of queue management is tail drop. That's a default behavior of many routers, but not all, where we simply keep everything in the buffer until we can. And here, this paradox is that sometimes it's good to not be conservative, but drop things even before. And we do this because we think that the sources are doing TCP. Now, if we combine all this, if we are in a network where all flows use TCP with ECN, and all routers support ECN, what do we expect? I close in a few seconds. Closing. The correct answer is C. There is no packet loss, no. We cannot guarantee that the packet is not dropped. If it's lost because your Wi-Fi link is broken, then even with congestion, with smart congestion management, you will not avoid that. Ideally, there should be no packet loss due to congestion, but the correct statement is in routers, because there might be congestion in other devices, bridges. You could have layer 2 devices that ignore all of this. They don't do anything, and they could drop packets here. They will once in a while drop packets here. This is bad. We try to avoid it as possible. We try to have the layer 2 networks be as loss-free as possible because they are not participating other than through losses here. Now, if we apply this to a very peculiar thing, which is called the data center, which is the visible part, perhaps some of you saw Ed's lecture last Tuesday. So the visible part of the internet is without data center, but the real part of the internet is happening inside data centers. So a data center is a room like we have, you might have visited it at the 2 weeks ago, we have two at EPFL. It's a room with lots of racks. And Google, Amazon, Facebook, etc. They live on this, but also smaller data centers like the EPFL data center, the CFF data center, switch drive, etc. What is special in data centers? Well, most traffic is TCP. For Google data centers, it might be quick sometimes. The latencies are very small, the order of microseconds or tens of microseconds. And you have a combination of really short flows with low latency with huge flows here. So the short flows are if you're crawling the index of Google to find how to, to give the answer to your Google query. And the jumbo flows are when you're doing background tasks, synchronization of some of the information that is used by the index or backup also here. Now, assuming you have been recently hired by Infomaniac to run the data center, so which version of TCP would you deploy? What's your preference? I close in a few seconds. And the majority says B and D, which are the two valid answers. In other words, you should do ECN, of course, right? In a data center, it would be stupid. So you have no wireless link anyhow. Everything is wired. Well, there are wireless links inside the components, but they are lossless. So it's stupid to lose packets simply because that's the only way you are found to send a signal to the source that should reduce the rate. Right? So the reason it's not done on the internet is that we don't control everything everywhere, so we kind of force everybody to use it. Plus, if there are wireless links anyhow, we will have the losses anyhow. But here, it would be stupid. So, of course, we want to do ECN in a data center. That's the first thing to do. And this is what data center TCP does, but with another improvement, which is done by this thing here. The goal of the data center TCP deviates from the cubic or Renault by avoiding the multiplicative decrease by 50% with Renault or 30% for cubic here. And the reason is that when we have huge transfer to do, even this small oscillation, here even 30% still means you're in a good fraction, or you're using 10 or 20, you're not using 10 or 20% of the capacity here. And since you're really trying to push performance as much as you want, you don't want to do this here. So what does it do? It uses a variant of the ECN framework where instead of simply selling a sound, like the DEC bit that we've seen is underlying all the congestion control of the internet, you go beyond and you do more like the TFRC protocol, the protocol I mentioned for video applications, where we want an estimate of the congestion probability here. So a source, instead of with the classical ECN, as soon as it sees one packet mark, it says, oh, I reduced the window. And then I will instruct the destination that I have marked it so that the destination knows and will not bother sending anything during one round trip time. I will not reduce again here. That's the classical use of ECN. We will do something else. The TCP source looks at all the marked packets, counts how many packets are, how many are marked, how many not, and tries to infer the probability of having a packet mark. And then the multiplicative decrease is by 1 minus p over 2. So if 100% of the packets are marked congested, will reduce by 50%. That's the additive, that's the multiplicative decrease of TCP Reno. If 1% of the packets are dropped, now remember this is for dual flows, right? There's so many hundreds of thousands of packets in a second. So you can have reliable statistics on P. If you have 1% of the packets that is dropped, you reduce, but by 0.5%. Yeah. So a minuscule amount. And if we do this, of course, it will improve over the large decrease and will give more efficiency. But how about fairness? If we have two large TCP flows competing for a bottleneck link, one uses DC TCP and the other does not, what will happen? I'll close the poll in a second. Yes, closing. So the majority thinks that DTCP will get much more, and a large minority thinks it's the other way around. Well, let's analyze this. I mean, first, even though the bandwidth is huge, the round trip time is so minuscule that probably cubic and Reno would be the same here. But, so we can compare to Reno. But Reno will decrease by 50% the window whenever it sees ECN signals, whereas DC TCP will reduce by something that is practically always less, right? If 1 minus p over 2, it's only if p is equal to 1 that this gives 50%. Whenever p is less than 1, the reduction will be smaller. So we will reduce much less. So DTCP increases the same way, DC TCP, but decreases by something that, except in the extreme case where the loss is catastrophical and everything is marked, not the loss, but the marking is catastrophical and everything is marked. In the normal operating regime, P is much less, and DC TCP reduces by much less. Therefore, a DC TCP connection gets more throughput than a regular TCP connection. Now, you could say inside the data center, I control everything. I could have only my own TCP traffic, which is actually true, but not exactly true. A large amount of the traffic inside the data center is internal traffic, then it will be DC TCP. But there are still some traffic that comes from the outside, that is going into machines that are inside the data center, and where the TCP source is outside, so outside your control. So it will not be DC TCP, it will be whatever TCP the user is using. Then we have the problem, DC TCP competes unfairly with other TCPs. So first thing, it cannot be deployed outside data centers. So we cannot run it in their global internet, or you could, but then you would have much better performance. And then somehow somebody will detect and it will cause problems. Even inside the data center, you need to separate the DC TCP flow. So this is typically done with class-based queuing that we will discuss in a second. So we will need to separate the flows by doing some kind of virtual networking using per class queuing that we will discuss in a second. Well, that's exactly the point. Let's discuss more bells and whistles in addition to the basics of TCP. Two things I want to discuss, TCP BBR and class-based queuing. So the first thing here that motivates TCP BBR is a version of TCP that is deployed largely by Google. And that is based on these observations here. What we call the buffer drain time is the time it takes. It's the time constant of a buffer. If you have a buffer of a certain size that is served by a line of a certain rate, the worst case queuing time, which is the buffer drain time, is the size of the buffer divided by the link rate. And the question is, what happens to this? Well, when you have an access network, my router at home, for example, on such drain time that is tens of seconds and probably minutes here. Right? Well, this is where the queue delay is a big problem. So we need to use ECN in such access networks. Otherwise, we will have this thing here. Now, in internet core links, the technology is such that if you want to increase the buffer capacity and increase the link rate, you need to increase the performance of your technology for actions. Right? If you have a given buffer size and you want to read this buffer and write it at twice the speed, you need to improve your technology by a factor 2. But if you want to keep the drain time constant, if you want at the same time to double the size of your buffer, then you need to reduce the nanometers of your technology, also just to make the buffer twice as large. So typically, you don't do that. So what happens here is that when the technology evolves, the buffer drain time decreases, and now in the internet, it is fraction of millisecond versus my and your router at home, which is seconds or tens of seconds here. So, which leads to some problem in essentially it's impossible to react correctly within a round trip time. So feedback control becomes a problem to net control links here. So this is one of the motivations for this variant of TCP called TCP BBR, which is widely deployed. But I give you a warning, it doesn't work well. So it is Google is doing experiments with us. Well, the idea is motivated exactly by that. And the idea is to estimate exactly the point A. How? By first controlling the rate, not the window. So not controlling the window, but the rate means I count how many bits are sent every millisecond, for example, and I put a limit to that. Whether those bits correspond to a packet being retransmitted or not, then you don't care. This is completely decorrelated from the sliding window mechanism here. Then we estimate the bottleneck bandwidth and the mean RTT separately. The mean RTT will give us what is when we should stop here, increasing the window, sending more data. And estimating the bandwidth will give us the rate at which we should send. And then we try to keep the amount of in-flight data. So the in-flight data is the data that is in the wires and in the buffers. It's between the source and destination, which at those very high speed can be a significant amount. So it is essentially the data that's in the buffers, and you want to keep them close to the bandwidth delay product that you've measured with the null RTT, which means you will be operating at buffers that are very small, close to this region. That's the idea. How is this implemented in BBR? BBR has two versions. There's a version that's doing exactly this, and there's a new version that is version 2 that is coming now that I'll say a few words about it. So the original BBR that was deployed in 5 years ago or 7 years ago does the following. So there is no reaction to losses on ECN, whether a packet is dropped or marked. TCP-BR doesn't care. It will estimate the RTT by measuring the round-trip time. So TCP is doing that. We've seen that TCP measures the round-trip time. For what purpose? For what basic purpose? Well, for correctly computing the value of the retransmit timer. And we will detect a loss by timeout in very extreme case, but the value of the timeout is based on an estimate of the RTT. So that's no added complexity. We also estimate what is called the bottleneck rate. So in this vision of BBR, they think that the network is a single link, which is more or less true. We've seen that when we analyze fairness, we have to be a bit smarter, but that's what is done in NBBR. And then the idea, the bottleneck rate given to this source is the amount of ACT data per delta T. Well, delta T is order of a second here. Now, this is a very academic view of the world because we know from the theory of bandwidth sharing that we've done in the past weeks of definition of fairness is that this concept works if you're alone. I have only one BBR connection. My problem is there's a physical bottleneck somewhere, and my bottleneck rate is whatever the physical bottleneck will give me. But if there's multiple connections that are using different parts of the network, what is the rate that is allocated to me by the bottleneck? I don't know. In fact, that's the result of utility maximization, which is the result of TCP. So we have chicken and egg problem, which is not solved by this. And we will see the consequence of not solving this. So it assumes that there is a well-defined bottleneck rate that I can measure. It's true, I can measure what I get from the network by measuring the throughput of my TCP connection. You will, with hyperf and things like this, you will be doing this in the lab. And then it does the following. It goes into different states, which are probe bandwidth, drain, and steady state. So probe bandwidth means I send at a rate. So I have estimated some rate here. I will send at this rate plus 25%. I go 25% above. And the goal is to see whether by doing that I get more. Then because the rates have been bad, to avoid filling the buffer, the next time slot, I will send 25% less, just in case I was overflowing the buffers to make sure I get closer to this A operating point. And then once I have done that, I send at exactly the estimated rate. And then I will reduce the rate and we re-estimate the round trip time here. And that's it. In addition, we still have a window, which is called max data in flight, which is given by this estimate of the RTT times 2. Right? 2 is a magic number that is given here. There's a few more details. There's something like a slow start, but the main thing is essentially we measure the mean round trip time, which is an estimate of the round trip time we would have when the buffer is not full, which is which of course is not what happens when I do this. And then we estimate also how much we get, which is the estimated bottleneck link, and then we send at this rate here. And if you have only BBR sources in certain settings, people have reported considerable improvement. So this is showing here something you can find here, giving on the y-axis of the green curves are the orange curves. No, the green curves are the throughput obtained by BBR. You see the plain lines, and the line below is cubic or Reno here. That does less because of those oscillations and the losses and the inefficiencies due to losing packets. So they have not compared to DC TCP because probably DCP would be also as good, but that's the first observation we can make. Not surprisingly, not having feedback from the network and this magical bottleneck measurement poses a number of problems. In the past, there have been several attempts to do a TCP measurement, a TCP signal that reacts to delays rather than losses here. And the problem is illustrated exactly by this figure here. Here, this is showing 6 BBR flows over a network that's a bit more public than what Google does, so done by papers that were published by colleagues in universities. And you see that depending on when and how the flows start and what is the topology of the network, you can have huge variability inside BBR, which has to do with the fact that you're trying to estimate how much the bottleneck is. I estimate a small, I say, oh, I am small, I'll try to stay around this small. And then it's very little. In fact, once in a while, it will increase by 25% during a short amount of time, but then they will quickly go down if that doesn't work well. So that mechanism is to be able to lead to some notion of fairness here. So we see that some flows can have several orders of magnitude more than some others using BBR. Worse than that, if you combine BBR with cubic or Reno, in these throughput values, it will be the same as Reno. You will see the Reno is the yellow thing. You see that BBR kicks out entirely cubic. Right? You can do this experience if you use some software or use TCP-BBR. For example, if you do a takeout experience, you download all your photos from Google. We'll be using probably TCP-BBR for doing this. And then you can forget about watching a movie at home while this is happening. If you're not using also BBR, and even if you're using BBR, you might be one of those things here. So there are several, after it was deployed by Google, the number of papers that have found that there are problems. In particular, what you find is, in fact, it still has a safety mechanism of 2 times the bandwidth delayed product. And in fact, they found that this is what dictates the performance here. So it's like having a fixed window that is not reacting to congestion. Of course, that is at the benefit of TCP-BBR flows when they're competing, but that's not very good. So after several years of deployment, so there is a problem. Now, I must say, it's only part of Google. Google uses QUIC, and QUIC uses also non-BBR congestion control flow. So not everybody inside Google does the same. Google is a large company. So they decided to reintroduce a reaction to ECN or congestion into BBR to make it something that will even be more complex. So stay tuned, perhaps in the coming years, we can study this. I will conclude with class-based queuing. Class-based queuing was mentioned already. We saw that inside a data center, you have to separate somehow by doing a virtual separation of your network between flows that uses DC-TCP and flows that don't. But you can imagine also other reasons for doing that. For example, what is called network slicing. If you're an operator like AT&T and you're offering a service to, for example, Tesla, to interconnect all the Teslas in the world, you don't want to build a physical network for Tesla. And you don't want either that if there is a lot of traffic on some part of the network, that this affects the Tesla, or vice versa. If Tesla decides to sell video to the users of Tesla cars, that would start congesting the network. So you want to separate somehow while using the same infrastructure. This is the concept of class-based queuing, and this is using schedulers in the routers. So the routers we've shown so far are on every output buffer, we have essentially a FIFO queue with red. That's the only variant to the FIFO property that we can have here. Instead of that, you can do queues that are, for example, the very simple systems are weighted round robin or deficit round robin. So packets are classified into classes. For example, if you know the data center example, if you know this is an internal packet, you know that either by observing the MAC addresses or the TCP, the IP addresses. So you need a classification mechanism, but we've seen that routers tend to do this anyhow. So you classify the packets between classes and you allocate weights to different classes. So with weighted round robin, for example, there is a weight W to class I, and then the router simply goes by round in a simplified version. For example, if class 1 has a weight of 1 and class 2 has a weight of 3, in every round, we will serve 3 packets of class 2 and 1 packet of class 1 and go on like this. So by doing this, we will allocate the resources proportionally to the weight. Per packet is not very adapted to the fact that packets are not all of the same size. So what is classically done in networks and is implemented in Linux, for example, is the same per bits. So called deficit round robin. We serve QIB, we allocate a quantum of bits, not 1 and 3, but for example, 10,000 and 3,000. And in every round, I serve 10,000 bits of class 1 or 3,000 bits of class 2. And it's called deficit because what do you do if you have a quantum of 10,000 and you can serve only 9,500, then you have a deficit of 500 that you will carry over to the next round. So that's the very simple. There's years of evidence of that. And this is used in data centers to separate flows. and also sometimes to isolate suspicious flows, or for, like I said, or for network virtualization by allocating a rate to one class. We can separate these. Now, this is not a strict separation. There is still the capacity of borrowing. If you think of weighted fair queuing, if during one round, class 1 has a rate of 1, class 2 has a rate of 3. If during one round, class 1 has no packet to solve, then we skip its turn, and then class 2 will have 3 packets, and then again 3. So class 1 can give available capacity that is not used by class 2. But there is a guarantee that it will always get at least 3 out of 4 of the capacity, roughly speaking. Here's an example that is used typically in industrial networks. In industrial networks where you have UDP applications for sensors, because TCP is not so appropriate to them. And then if we have some UDP applications, in a case like this, streaming at 1 megabit per second each, then we can decide to allocate 3 deficit round robin, for example, a rate of 2.5 megabits per second for the red streaming traffic, and a rate and the rest to TCP connections, for example, that I use for the rest of the business here. And I will conclude on this very fast quiz. Yes, I have minus 1 minute to conclude. If we're in this setting, now we use the class-based queue to separate the UDP streaming applications from the normal applications. Two PCs that are trying to transfer data with S1, and assuming the RTT are the same, how much of will the 2 PCs get in this setting here? I close the poll. The correct answer is B, and the reason is intuitively simple, but mathematically perhaps a bit more complicated. Well, this is what will happen from the viewpoint of the blue. The red is sending at exactly 1 megabit per second. So the blue has 7.5 guaranteed, but not 9 available, in fact, because from borrowing. So it's the same problem we did before. We have 2 flows that are sharing a network where the capacities are not the physical capacities, but 9, 8, 8. So how much will they get? Well, because their round trips are the same, we can do several things. We can check the maximum fair allocation and the properly fair allocation. We see that they give the same, since TCP is in between. If they're the same, they should be the same. Or you cast that as a utility maximization problem. You need to maximize the sum of the utility subject to the constraints. Those are the 3 constraints. They're all equivalent to this. So you have to maximize U of x1 plus U of x2 because they have the same round trip time. They have the same U. So the optimal should give the same value to x1 and x2. It should be Pareto efficient, so it should reach quality that gives 4 megabit per second. But that's the end of this story and of this lecture for today. Thank you very much.